Hello everyone. So, today we are going to do a tutorial session on Routh Hurwitz stability criteria. So, we are going to do some problems based on the theories we studied till now, like how to determine stability, how to find out unstable systems in using Routh Hurwitz criteria. We will also see special cases on as 0 as the first element and also 0 in the entire row. Now, so we start with the basic problem. How to determine stability of a system. So, determine the stability of the system whose characteristic equation is s to the power 4 plus 2s cube plus 8s square plus 4s plus 3 is equal to 0. Okay. Also comment on the location of the roots of the system. The poles of the system. Okay. So, this is our characteristic equation. Now, for the characteristic equation, the Routh array will be, so we take first s to the power 4, then s to the power 3, okay. Now, s to the power 4 first 1, alternatively 8 and then 3, and for s to the power cube as cube, so 2 and then 4 and then 0. So, as we saw that this term comes from multiplying this 2 minus multiplying this 2 divided by this factor. So, we can do this way, that 1 by 2 divided by, just take this as a determinant. So, 1 by 1 2 and 8 4. So, what we are doing basically, this is a n, this is a n minus 2, this is a n minus 1, this is a n minus 3. So, what we are doing is a n into a n into a n minus 3 minus a n minus 1 into a n minus 2 divided by a n minus 1 minus. So, basically there the minus will come here and this will be plus. So, that is what we learned. So, here we get minus half . 4 minus 16 . So, here it will be 3. So, similarly, if we do one 2 and 3 0, we will get 3. So, here we get 3. Now, s to the power 1. So, similar way 6 into 4 minus 3 into 2, that means n s to the power 0 will be just 3. So, we see that there is no sign change. So, just let us write the first column only. So, the first column is 1, 2, 6, 3, 3. So, the signs are positive, positive. So, all are positive. So, there is no sign change. So, we can say the system is stable. Sorry, all the roots lie in the left hand plane, hence the system is stable. Okay, so second problem we are going to do on how to find out if the system is unstable or not. So, second problem will be, so using Routh Hurwitz. So, this is RH means Routh Hurwitz. Find the stability of the system with characteristic equation s to the power 5 . So, it will be 3s cube. Okay. So, Routh array for the given system is first s to the power 5, then s to the power 4, s to the power 3, s to the power 1. Okay. So, 1, alternatively 3, then 16, and here comes 1, 9 and 10. So, this point will be, so this is easy, 3 minus 9, so it will be minus 6, 1 into 16 minus 10, so this will be 6. Okay. Now, this is 10. 10 into 6, 60 minus, yeah, so 12, and this is 10. So, now the first column is 1 1 minus 6 10 12 and 10. So, positive negative so there are two sign changes from here and from here. So, we learned that number of sign change is equal to number of roots in the right hand plane. So, number of therefore is 2 and the system is okay, and the system is unstable. Now, we solve a problem if the first element of the row is 0. So, okay. Let us consider the characteristic equation of a system s to the power 5 plus s to the power 4 okay. Now, the Routh array is so first will be 1, then 2, then 3, here will be 1, 2 and 5. So, 2 minus 2 this will be 0 and 3 minus 5 this will be minus 2. So, we see that this term is becoming 0. So, what we learnt is we will replace it by a positive number, small positive number epsilon here. So, the 0 is replaced by small positive number epsilon. Now, so this will be epsilon. Now, so the next term becomes 2 epsilon plus 2 by epsilon, and here we get 5. So, calculating we find this will be 5 e to the power 2 plus 4 epsilon plus 4 by 2 epsilon by 2, and s to the power 0 it will be 5. Okay. So, what we do is now we consider these terms, we check the signs considering that epsilon is a small positive number tending to 0, but it is positive. Okay. Then 2 epsilon by plus 2 epsilon, this is a positive quantity, because you can write it as 2 plus 2 pi epsilon. So, this is greater than 0 and epsilon is positive. So, this is also greater than 0. Now, the other term, this one, limit epsilon tends to 0 minus of 5 is equal to minus 2, that is negative. Okay. Negative. Now, we consider the first column. First one is 1, so positive, second is positive, third one is epsilon. We can assume that epsilon is a small positive quantity. So, this is positive, this is also we found positive. Now, this quantity we found that this is negative. So, this is negative and finally 5, so positive. So, there are two sign changes here and here. So, number of roots in the right hand plane is equal to 2 and the system is unstable. So, let us consider one example where the entire row is 0. So, how we use the auxiliary polynomial and find out the roots and determine the stability of the system. Okay. Okay. So, let the characteristic equation be given by s to the power 6 plus 3 s to the power 5 plus 5 s to the power 4 plus 9 s cube plus 8 s square plus 6 s plus 4 is equal to 0. So, construct the Routh array s to the power 6, s to the power 5, s to the power 4, s to the power 3, s to the power 2, finally s to the power 0. Now, first comes 1, then 5, then 8, and then 4. And here is first element is 3, then 9, and then 6. Okay. So, here will be first element will be 2, 15 minus 9 by 3 are 2, and then 6. Okay, and last term is 4. Okay. So, now for s to the power 3 all the terms are 0, 18 minus 18 0, 12 minus 12 0. Okay. So, we get here, so 0. So, what we learnt is we consider a auxiliary polynomial S, and we go to the immediately upper row. So, which is for s to the power 4. So, here it will be 2 s to the power 4 plus 6 s square plus 4, and the auxiliary equation can be written as s to the power 4 plus 3 s square plus 2 is equal to 0. So, we take common 2. So, we divide all the terms by 2 and we get this equation. So, the we find what we now do is we find the derivative of the auxiliary equation, that auxiliary polynomial, that is d a s with respect to d s, that is 4 s to the power 3 plus 6 s plus 0. Okay. So, the coefficients were will be placed by 4 and 6. Okay. So, 4, 6 and 0. For s to the power 2, the terms will be 3 and here will be 4. Now, think, yeah, so 18 minus 16. Okay, so it will be 2 by 3 and here it will be 4. Okay. So, just consider the first column. So, there are no sign changes. So, all the terms are positive, 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 yeah, positive. So, there is no sign change. That means there are no roots in the right hand plane, but we can't for determine the stability of the system, we need to find out the roots of the auxiliary equation, because we learned that the roots of the auxiliary equation is also the roots of the characteristic equation. So, the roots will determine the stability. So, here we can see that s to the s square plus 1 into s square plus 2 equal to 0. Okay. So, for s square plus 1 equal to 0, we get s is equal to plus minus j into 1, and for s to the power 2 plus 2 yeah. So, there are 4 roots on the imaginary axis. So, if we construct we just draw the S plane, and this is j omega, this is sigma. So, and there is one at plus j, one at minus j, and one as j 2, one as plus j 2 square root of. What we learnt in the first lecture of module 4, that if there are non-repeated roots on the imaginary axis, then the system will be marginally stable. So, here we find that there are 4 roots on the imaginary axis, but none are repeated. So, the system is marginally stable. Okay. So, done. Now, some problem on feedback. Now, we do some problems on the determining the gain of the feedback systems, what we learnt in lecture 3 of module 4. So, how we will see how we can use Routh Hurwitz criteria and apply it in feedback systems to determine the gain. So, quickly we will do. So, this is problem number 5. So, let the characteristic equation of a closed loop feedback system B is to the power 4 plus 2s cube plus 4 plus k square So, first we construct the Routh array. S to the power 4 So, first term will be 1, second term is 4 plus k and third term is 25. Okay. Now, here first term will be 2 and second term will be 9. So, here we get is k minus half and here 25. Now, just calculate, after calculating we will find out that this term is 18k minus 109 by 2k minus 1. And this term will be 25. Okay. Now, if we want the system to be stable, so let us find out what will be the range. So, what will be the range of k for the system to be stable. Okay. So, for stability what we know is that all the terms should be positive. So, k minus half, first condition is k minus half should be positive, that means k is greater than half, and second condition is, so this term will also be positive. So, 18k minus 109 by 2k minus 1 is greater than 0, that implies that k is greater than 109 by 18. Okay. Now, definitely this value 109 by 18 is greater than half. So, the system will be stable when the value of k is greater than this. So, system is stable for k greater than 109 by 18. Yeah. So, similar problem, if we just give a parameter to the system and we tune it and find out how the parameter, what will be the range of the parameter such that the system will be stable or marginally stable or unstable. So, we consider another example like that. So, yeah. So, characteristic equation is to the power 3 plus k a square plus k minus 3 s plus 4 is equal to 0. So, we have to find out what will be the range of k for the system to be stable and b marginally stable. Okay. So, Routh array S cube first term is 1, then k minus 3 and this is k, this is 4. So, this term will be k square minus 3k minus 4 by k and this term will be 4. So, for stability the conditions will be for the system to be stable. Okay. So, all the elements of the first column should be of the same sign. So, should be positive here. So, k first condition is k is positive and second condition is k square minus 3k minus 4 by k is greater than 0. So, since k is positive, it implies that k square minus 3k minus 4 is greater than 0, that is k minus 4 into k plus 1 is greater than 0. Okay. So, here we find that k is greater than 4 because k can't be greater than minus 1, because that condition if it lies between minus 1 and 0. So, it does not hold first condition. So, k will be greater than 4 if the system is to be stable. Okay. So, part A is done. Now, part B. So, we do part B. So, for marginally stable, this term will be 0, that k square minus 3k minus 4 is equal to 0, that is when k is equal to 4. Okay. Now, the auxiliary polynomial is equal to 4a square 4, because k is equal to 4, then dA ds 8s plus 0. Okay. So, replace k by 4, replace this by 8, and this will be 4. Okay. Now, we find that the all the sign elements of the first column are of the same sign. So, there are no roots in the right hand plane, and the roots of the auxiliary equation a square plus 1 taking 4 common equal to 0 are s is equal to plus minus j 1. So, there are two roots on the imaginary axis at plus j 1 and at minus j 1, okay. And then the system is marginally stable with oscillating at the frequency of omega is equal to 1 minute per second. Yeah. So, k will be 4. Problem number 7. So, we find the number of roots which are in the left of the axis s is equal to minus 1. Okay. So, how to do that? So, we have to find out how many roots are there at the left of s is equal to minus 1. So, we consider a dummy variable s n such that s n is equal to s plus 1. Now, if we write the characteristic equation in terms of s n, so it will be s n minus 1 whole cube plus 4 s n minus 1 whole square plus 6 s n minus 1 plus 4 is equal to 0. So, if you calculate, you will find that the characteristic equation in terms of Sn will be Sn to the power 3 plus Sn to the power 2 plus Sn plus 1 is equal to 0. Okay. Now, Routh array for this system, Routh array for the new equation is Sn to the power 3, Sn to the power 2, Sn to the power 1, to the power 0. Okay. So, 1 1 1 1. So, the entire row is going to be 0. So, we consider the auxiliary equation S is equal to S to the power 2 plus 1 is equal to 0. Okay. So, ds is equal to 2 S plus 0. So, this is 2 and this will be 1. So, all the elements of the first column are positive. So, there are no roots on the right hand side of S is n, it is no roots . S is equal to minus 1. Okay. Now, for the auxiliary equation, if we find the roots, so we will get so Sn square plus 1 is equal to 0, that is Sn is equal to plus minus j. So, what we get is that there are two imaginary roots on Sn is equal to Sn. So, imaginary axis of the shifted plane Sn. So, Sn plane is plus, this is j omega sigma here. Okay. So, there will be two roots. Okay. Now, if we see the entire picture in the S plane, that is not in Sn plane, but in S plane, what we are going to see, find that. So, this is our original sigma, this is our j omega. So, we have shifted the axis to minus 1 and there are two roots at minus j plus minus 1, or better to write minus 1 minus j minus 1 plus j. So, there are two roots here. So, this kind of axis shift is very useful in systems where there are number of imaginary complex roots. So, more than one complex pair of roots are there. So, if we are going to determine the relative stability of the system based on how the roots affect on the damping of the system. So, this axis shift method using Routh Hurwitz criteria will be helpful. And the final problem for today's tutorial. So, final problem for today's tutorial. Now, let us consider the same problem we did in the module 3 for time response. So, and this is the error ES. So, in that problem for time response, what we found is if the steady state error is going to be 0, but not for ramp input. So, H will be 1. So, we can modify the loop gain of the system as GS is equal to K into S plus 2 by S, since H is equal to 1, S plus 1 S square plus 10S plus 41. Okay. And the characteristic equation will come from 1 plus GS. So, the numerator of the this 1 plus GS, that is so the numerator of this term. So, this part. So, this is the characteristic equation of the system, and so we ought to find out what will be the range of k for what values of k the system is stable. Okay. So, numerator will be the characteristic equation.
You told that.
Yeah. So, the characteristic equation is the numerator of the part of 1 plus GS, that is CE is S to the power 4 plus 11 S cube plus 51 S square plus 41 plus K S plus 2 K is equal to 0. Okay. So, we form the Routh array. So, the first term will be 1, second 51, finally 2k, and here it will come 11 and 41 plus k. So, this term will be 520 minus k by 11, and this is 2k. S to the power 1 will be minus k square plus 237k plus 21 So, we have to find the values of k for which the system is stable. So, there are 3 terms related to k in the first column. So, the first condition will be 520 minus k by 11 greater than 0, that implies k is less than 520. Second condition is minus k square plus 237k plus 21320 by 520 minus k will be greater than 0. So, from condition 1 this term is greater than 0. So, we have to make this term greater than 0. So, let us consider the quadratic equation k square minus 237 k plus minus 21320 is equal to 0. So, the roots of this equation plus 237 plus minus, just calculate this, you will get 141,449 divided by 2. So, if this term is going to be greater than 0, so what we need is k should lie between plus 237 plus root over 141,449 by 2 and 237 minus root over 141,449 by 2. What we find that so this is almost equal to 367. So, the upper limit of k now reduces to from 520 to 367. Okay. Now, the third condition comes from write it here. Third condition is k is greater than 0. So, this part is negative. So, this part will be replaced by 0. So, the range of k is now 0 greater than less than k less than 367. So, within this range the system will be, the entire closed loop feedback system will be stable. That is it. Thank you.